Ever wonder what the fundamental building blocks of, well, you are? We're talking about these tiny molecules called amino acids. And, believe it or not, each one has its own dynamic chemical personality. They're the architects behind everything, from your muscles to the enzymes that break down your lunch. So today, we're going to pull back the curtain and uncover their secret life.
All right, so here's our game plan. First, we'll see how these guys can be both acids and bases at the same time. Then we'll get into the pH rulebook that dictates how they act. We'll meet this really cool thing called a zwitterion, follow one specific amino acid, alanine, on its journey, and finally, we'll see why all of this is so incredibly important. It's gonna be great.
All right, let's kick things off by looking at the basic blueprint, the fundamental design of every single amino acid out there.
So when we're just hanging out at our body's normal pH, which is around 7.4, every amino acid has these two distinct chemical handles. You've got a negatively charged part, the carboxylate group, and a positively charged part, the amino group. And trust me, these two groups are the key to everything we're about to talk about.
And this right here, this is what's so cool about them. You have this core duality. The carboxyl group, that's your acid. It's given away a proton. And the amino group, that's your base. It's grabbed a proton. So you've got an acid and a base in one tiny molecule. It's this two-faced nature, this chemical personality split, that lets them do so many amazing things. Okay, so we know they have these two different groups, but what happens when you change their environment, say by making it more acidic or more basic? How do we predict what they're going to do? Well, it turns out there's a rule book for that. And that's the big question, isn't it? How can we predict exactly when these groups will decide to gain or lose their protons? This is like a central question in biochemistry. We need a reliable way to know when this proton handoff is going to happen. And lucky for us, we've got just the tool for the job. So our first tool is something called the acid dissociation constant, or Ka for short. All it is really is a measure of how strong an acid is. A bigger Ka just means a stronger acid, one that's more eager to give away its proton. Think of it as the raw data, the spec sheet on just how acidic that group is. And now for the main event, the Henderson-Hasselbalch equation. Okay, I know it looks a little intimidating, but don't worry about the math itself. Let's just focus on what it does. This equation is our biochemical rulebook. It takes a neat little number called the pKa, which comes from that K value we just saw, and turns it into a super practical tool. It lets us predict exactly how an amino acid is going to behave at any pH we want. This is how we make sense of the chaos. Okay, now that we have our rulebook, let's see what happens at a really specific, really important point in an amino acid's life, a point of perfect balance. Check out this molecule right in the middle, form 2. That's our buddy alanine, just sitting in a neutral solution. Now notice what's going on. It still has that positive charge on the amino group and that negative charge on the carboxyl group. They're both there, but here's the kicker. They perfectly cancel each other out. And this special state, this perfect electrical balance, has a fantastic name. It's called a zwitterion. It's a German word, basically meaning hybrid ion, which is just a perfect description, right? It's a hybrid, carrying both a positive and a negative charge at the exact same time. So here's the most important takeaway. Even though it has charged parts, the molecule as a whole is electrically neutral. The net charge is zero. Zilch. Nada. It's like the amino acid's neutral disguise, and it's a super useful property that scientists actually use to separate out different proteins in the lab. All right, let's put all these pieces together now. We're going to follow one amino acid, alanine, on a kind of journey. We'll systematically change the pH of its environment and just watch what happens. Watch how it transforms.
You see, depending on the pH, alanine can have one of 3 different identities. In a really acidic environment, it's form I, with an overall positive charge. At a more neutral pH, it puts on its zwitterion costume, form 2, with that 0 net charge. And then, if you put it in a really basic solution, it switches to form 3 with a net negative charge.
And this graph, this titration curve, it's basically the whole story of alanine's journey in one picture. On the bottom, the x-axis, we're tracking the pH. And on the side, the y-axis, we're seeing how much base we've added. Now, see those two parts of the curve that are kind of flat? Those are super important. Those are the buffering zones, where the pH just refuses to change much at all. Let's break down the key moments here.
Okay, so there are 2 critical points on this map. First, at a pH of 2.3, we hit pK1. That's the exact moment the carboxyl group gives up its proton. Then, way up at a pH of 9.1, we hit pK2, where the amino group finally lets go of its proton. And right around each of these pKa values, the amino acid is an amazing buffer. It just soaks up any extra acid or base you throw at it.
And right there in the middle, at a pH of 5.7, we have the isoelectric point, or Pi. This is the sweet spot. It's the pH where the zwitterion form is king, and the molecule has that net charge of 0 we talked about. It's the point of perfect electrical balance. And hey, quick tip, you can find it just by averaging those two pKa values.
So we've just watched this really cool molecular transformation. But this isn't just some abstract chemistry trick, right? The big question is, why does any of this matter? Why is this ability to gain and lose protons so incredibly important in the real world?
Let's go back to that flat part of the curve, that buffer region. This is really where the magic happens. In this zone, right around the pKa, the solution just resists change. It can absorb extra acid, it can absorb extra base, and the pH barely budges. It really is like a chemical sponge for protons, and its whole job is to maintain stability.
And that stability, it's not just nice to have, it's absolutely vital for life. I mean, our own blood uses a bicarbonate buffer system that works on these exact same principles. Its job is to keep our blood pH locked into a super narrow, super safe range. This isn't an exaggeration. This chemical buffering is literally what's keeping us alive every single second of every day.
And it's not just in our bodies, it's in our medicine too. Take something like aspirin. It's a weak acid. In the superacidic environment of your stomach, it stays uncharged. And because it's uncharged, it can easily pass through cell membranes and get absorbed into your bloodstream. So the drug's ability to even work depends entirely on its charge, which, as we've seen, is all about the surrounding pH and its pKa.
So think about it. We've just seen how one single, relatively simple amino acid has this incredibly rich and complex chemical personality. It can be an acid, a base, a buffer. It's a real shapeshifter, which leads to one final kind of mind-bending question. If just one of these little guys can do all that, what in the world happens when you string hundreds or even thousands of them together to build a massive, complex, folded protein?